Hello and welcome back to this session. In this session, we are going to go deeper into the programming side of equation in terms of when you come up with some of the algorithms and you can take the time trajectory and you are using Newton's second law of motion, and then you want to calculate using finite difference methods, then you also need to understand how to run the molecular dynamics code. Before we begin, we know that MD molecular dynamics simulation for discoveries in science has a very wide application field. It is a unified study of all kinds of physical properties, which we will look at today in terms of how in a particular molecular dynamics code we are able to calculate some of these physical properties. We will go take a deeper dive into that as well and understand how these codes really work and how they lead to the data that we are looking for. But the important part here is that we can calculate thermodynamic properties, structural properties, mechanical properties, vibrational properties and transport properties. And I am going to put a little bit more emphasis on coming sections in the area of vibrational properties. So, if you look at with just 100 atoms we can or 200 atoms we can calculate a lot of these properties. We have looked at VMDL simulations and they are pretty realistic, although they may not connect exactly with the experimental numbers, but the trends are very well captured in terms of the physics of the complex situations. And because it is molecular dynamics, we have complete control on the system. It is a deterministic. We can change any properties, and with the trajectories we are able to now calculate ensemble averages. And as you know, the molecular dynamics in particular works in the equilibrium part of the thermodynamics. So, if you look at equilibrium situation, then we are looking at the properties that have to reach equilibrium state, and then we can apply ensemble average and the time average. So, the time average that we are calculating in the trajectory, that becomes equal to the ensemble average, and that is the basic principle applied, which is called the behavior, which is called ergodic behavior of the system. So, this ergodicity is very important for what we call is a system that is equilibrium thermodynamic system. There are also systems that are non-equilibrium and they are called chaotic system. You will also see that computational methods can be applied onto those situations as well. But for our discussion in molecular dynamics, we deal with the ergodicity as a basic principle, and also then we are able to take time average of the trajectories and convert that into an ensemble average. So, in the last few sections we have looked at the machinery that is applied in molecular dynamics, which is statistical ensembles and statistical mechanics, and that allows us to look at the Boltzmann distribution of each particle. Then we look at the partition function, and with that partition function we can calculate the entropy of the system from micro state to the macro states. And so, when we create the assemblage of micro states and do look at their trajectory in the time space where the micro states are able to sample the entire phase space, then we are able to get good statistics and apply the principle of statistical mechanics. We also looked at that we can then apply different ensembles like microcanonical ensemble where energy is constant. We can use that canonical ensemble where temperature is constant, or isothermal isobaric ensemble where temperature and pressure constant, and we can also do grand canonical ensemble where the chemical species or the chemical composition is constant. So, we can also look at in grand canonical ensemble different kinds of chemical species and look at the chemical reactions. So, what we are going to do now is look at the Newton's equation of motion, and we looked at the trajectory in a 3-dimensional space x, y and z. We also looked at the vector space where we can put out some equations in order to look at a arbitrary vector r I j and the components of that r I j in x, y and z direction with the unit vector x cap, y cap and z cap, and that kind of formulation leads us to now a situation where now we can create a second order differential equation, ODE, ordinary differential equation, and then provide initial value and the boundary value problem. Now, ordinary differential equation can work very well with only initial conditions. However, in this case, because we are dealing with different kinds of thermodynamic ensembles, we also have to provide what we call as the boundary conditions. We looked at the boundary conditions there, integration of motion, where we have expansion of the Taylor series, and we said that we can go to third order, fourth order, fifth order, or sixth order. And so we can, and these orders essentially represent how many factors you are considering in the expansion of the Taylor series. So if you look at depending on where you cut off this expansion of the Taylor series, you can create different kinds of error. Number one is truncation error, because after a second term, let us say if you stop a third term where we are looking at a quadratic equation or second order differential only up to the 3 steps in Taylor series expansion, then we are creating some kind of truncation error. And also we are creating round off error based on how we put data in the computers and how many floating points we consider in order to calculate different parameter. We also understand that molecular dynamics depends on certain approximations, like Born-Oppenheimer approximation, where it says that the atom is located at the nucleus and all the electronic states are essentially put right at the nucleus of the atom, and that is where we can create this assumption of point charge, that the charges are at certain location close to the nucleus, and they are all connected. The electronic states are essentially connected with the nucleus, and that is why we can take particle trajectories and look at them without worrying about the electronic states. If we had to look at the full quantum mechanical description of particle, where we use Schrodinger equation, if you collapse all the electronic wave functions, then it comes down to Newtonian mechanics. So this is where we can take a generalized quantum mechanical situation, create this Born-Oppenheimer approximation, then we are in the Newtonian regime, and we can use then various ways of looking at the trajectories. We also looked at different kinds of finite difference algorithms. We looked at Verlet algorithm, where it was essentially central difference method. You go positive step and negative step and integrate in the middle, and that is where you can come up with Verlet. We looked at the leapfrog, where you can go to half step on the top. Then we also looked at velocity Verlet, where we calculate the velocities, and then also taking much longer expansions of the Taylor series by creating Beeman algorithms. So if you look at all of these techniques, and specifically the gear predictor corrector algorithm that we are going to use in some of the software that we will discuss today for the molecular dynamics simulation, we will look at the predictor, evaluator, and the corrector steps. So there are 3 steps. So I think these are the issues that we want to discuss now. We want to understand how we set up a system, what are the initial parameters, how we initialize the system, provide all the parameters related to the potential energy function, because we have to do a force calculation. Once we do the force calculation, then we have to find out the next time step, what is the position of the particles, and then we have to correct those positions by applying corrector based on, let us say if we choose 5th order predictor corrector algorithm. So these are the models which are very important. Now we are going to see how we actually implement that in the sense of software. So I will take you to an anatomy of a molecular dynamics software code. So even if you may not have background in, let us say, computer science and writing software, you will understand when you are using a black box molecular dynamic system like NAMD, or you are using a CHARM or one of the AMBER. These are the packages available out there for doing molecular dynamics calculation and molecular mechanics. Then you need to understand what are the guts and how these programs work. So you will get a good understanding of these in the coming sections. Thank you.